Welcome. This video is on geometric sequences. A geometric sequence is a sequence in which the ratio between a term and its preceding term is a constant. In other words, what number are we multiplying a term by to get to the next term? Another way we could look at it is dividing a term by its previous term, and if that number is the same for any term and its previous term, then it's a geometric sequence. So here's an example. 5, 10, 20, 40. What number do you multiply by to get to the next term? Yes, 2. Or if you take any term and divide it by its previous term, you should get 2. 10 divided by 5 is 2. 20 divided by 10 is 2, etc. So that's the notation for saying a term divided by its previous term equals r. So we're going to use the letter r, and that represents the common ratio. Okay, so in this example, the common ratio is 2. Here's our formula. Hopefully your teacher doesn't make you memorize it. In this lesson, we're going to have 3 formulas. Okay, so here's the general term of a geometric sequence. The general term is a sub n equals a sub 1 times r to the power n minus 1, where a1 is the first term and r is the common ratio. Okay, so make sure you write down that formula. We're going to use it. And the main thing from this page to know is that a1 is the first term and r is the number that we multiply by to get to the next term. Or it's a term divided by its previous term, and if that number is the same, then that's r. So any term divided by its previous term is equal to r. Okay, so here's our first example. We have a geometric sequence 2, 6, 18, 54. You could probably look at it and recognize what r is. What number do you multiply by 2 to get to 6? What number do you multiply by 6 to get to 18? Okay, so here's our formula. an equals a1 times r to the power n minus 1. We need to find a1 and r. So what's our a1? a1 is 2, the first term. How about r? Right, r is 3. Again, it's a term divided by its previous term, so 6 divided by 2 is 3. 18 divided by 6 is 3. You could keep going if you wanted to. So plugging those two numbers into the formula, replace the a1 with 2 and the r with 3. That's it. We're all done. We cannot multiply the 2 times 3 because the 3 has an exponent of n minus 1, and 2 and 3 are not the same base. If they were the same base, then we could use our rules for exponents and add the exponents. Okay, so that'll come up on our next couple of examples. But that's it. Replace the a1 with 2 and the r with 3, and you're all done. Okay, here's our next one. 8, 32, 128, etc. Same directions. Find the general term. So write down your formula. an equals a1 times r to the n minus 1. We need a1 and r. What is a1? Right, a1 is 8. And r, what is our r? 8 times what number is 32? 32 times what number is 128? So a1 is 8 and r is 4. Now plug those into the formula. Okay, so an equals 8 times 4 to the n minus 1. On the last example, we were all done because you could not do anything with the 2 and 3. On this one, we can. We could rewrite both of those numbers using the same base. The base that we could use is 2. 8 is 2 to the third. And 4 is 2 squared. So rewrite both numbers using a base of 2. So 8 is 2 to the third, and 4 is 2 squared. Now on the second number, 2 squared to the power n minus 1, you're going to distribute the 2. So when we have a base to an exponent raised to another exponent, you multiply the two exponents. So that gives you 2 to the 2n minus 2. Now that we have both bases the same, they're both 2, now we could use our rule for exponents. When the bases are the same, then we add the exponents when we're multiplying. So it's 3 plus 2n minus 2. And now we could add like terms. So 3 and negative 2 is positive 1. That gives us our final answer of 2 to the 2n plus 1. So it's a little bit of algebra there, right? Some rules with exponents. Okay, here's our next one. The same thing I think is going to come up on this one. If you want, you could pause the video and try to work it out. Okay, our formula, an equals a1 times r to the n minus 1. What is our a1? Our a1 is negative 3. How about our r? R is also negative 3. So now we're going to plug those two numbers, which are the same number, into our handy-dandy formula. So an equals negative 3 times negative 3 to the n minus 1. The bases are the same, so therefore we could add our exponents. The exponent on the first negative 3 is a 1. So we're going to add 1 plus n minus 1. 1 plus n minus 1, the 1's will cancel, and we're just left with n. So there's our final answer, a sub n equals negative 3 in parentheses to the power n. It was important to keep the negative 3 in the parentheses because we have an exponent. Yes, not having the parentheses around it creates problems. So make sure each negative 3 has parentheses around it when you're working it out. Okay, here's our next example, a little bit different this time. Find the 15th term for the sequence, the geometric sequence, 2, 6, 18, 54. So this time we only want the 15th term. That's what n is, right? N will be 15. So we have our a1, which is 2. How about r? Right, r would be 3. And we have our n, So we're going to plug those numbers into our handy dandy formula. You could put the 15 at the end, or you could put it at the beginning. It's totally up to you. So work that out. So that's 3 to the power 14 times 2. So n is 15. A1 was 2, and r was 3. So 2 times 3 to the 15 minus 1. 15 minus 1 is 14. 3 to the 14th, you got to use your calculator. And then multiply that by 2, and you should get 9,565,938. Okay, this example is very similar to the last example. Find the ninth term for the geometric sequence, -4, -24, -144, etc. So we're going to use our handy dandy formula. A sub n equals a1 times r to the n minus 1. We need a1. A1 would be -4. How about r? Yeah, r would be +6. If you take a term and divide it by its previous term, you're going to get +6. So you could take those two numbers. If you wanted to plug in n right away, you could. N is 9. If you want to wait, get the general term, and then plug in 9, totally up to you. So let's plug in -4 and 6 right now. Okay, so that's that. A sub n equals -4 times 6 to the power n minus 1. Okay, now our next step is plug in the 9 for n. So 9 minus 1 is 8, and you're going to have to do that on your calculator. So 6 to the 8th is a large number. Multiplied by -4, and you should get -6,718,464. Not too bad so far, right? Okay. Now we're going to talk about adding the terms of a geometric sequence. To find the sum of a geometric sequence, we need to know the first term, which is a1, the common ratio, which is r, and the number of terms, n. So these are two formulas for the sum. They're actually both the same. There's many forms. These two are the most common formulas, I think. It just has to do with distributing, or maybe factoring out a -1, because some people don't like it to be 1 minus r instead of r minus 1. So either one of those formulas are the same. Your teacher might also give you another formula, which is it's still the same. So find the sum of the first 15 terms, that's our n, of the geometric sequence 2, 6, 18, 54. It's infinite, but we only want the first 15 terms. So let's write down one of the formulas. I'll write down this one. A1 times r to the n minus a1 all over r minus 1. Now, you probably could find all 15 terms and then add them all up on your calculator, and you would get the correct answer, and it wouldn't take too much effort. However, the directions on a test will probably be to show using the sum formula, S sub n, so you still have to show the work. Okay. Because calculators are limited, they're not computers, these numbers could get very large very quickly. So we might not ask for the first 150 terms like we did for arithmetic sequences. Because what will happen is, in many sequences, it'll say overflow error. The calculator won't be able to handle it. or it might put it in scientific notation, which is then an issue as well. Okay, so we just still show the work, and we'll probably keep the numbers pretty low because of the limitations of calculators. All right, A1 is 2, right? First term is 2. Our R is 3, and N is 15. So plug all those numbers into your calculator. It'll be S sub 15 equals 2 times 3 to the 15th minus 2 all over 3 minus 1. Now you should be able to just type that right into your calculator. You probably have a fraction button, so use your fraction button, type in the top and the bottom all at once, and then use your calculator, and you should get 14,348,906. Okay, so not a lot of work to show. You're just basically showing that you're putting in the numbers into the formula and working it out on your calculator. Another problem very similar. You might want to pause the video, work it out, and then come back when you're ready. Okay, handy dandy formula. Our A1 is 64. Our R, well, we have to divide the second term by the first term. So 32 divided by 64 will give you 1/2. So our R is 1/2. It's not 2, because if it was 2, you would be multiplying 64 times 2 to get the next number. We're actually dividing by 2, so that really means 1/2. And our N is 10. Plug those into our handy dandy formula. Use our calculator. It might come out to be an improper fraction. Change it to a mixed number. 127 and 7/8. Again, it's always good to have a decent calculator that can handle some fractions. Example 8. Find 3 plus 33 plus 363 plus 3,993 plus plus 643,076,643. Okay, so we're trying to find the sum. On the last section, we talked about arithmetic sequences, and this section we're talking about geometric sequences. In the problem, it doesn't say what kind of sequence it is. You need to be able to recognize which one it is. Of course, this is a section on geometric sequences, so it's probably an example of a geometric sequence. But in arithmetic sequences, we were looking for a common difference. We were looking for what number do you add to each term to get to the next term. And so you could see this is not arithmetic, because to get from 3 to 33, we would add 30. And then to get from 33 to 363, we would have to add 330. So it's not arithmetic. It does not have a common difference. This should have a common ratio, though. If you divide a term by its previous term, what is 33 divided by 3? That's 11. So then try 363 divided by 33. You might want to do it on your calculator. That should also give you 11. So we could see that this is a geometric sequence, and the common ratio is 11. On a test, it may not tell you that it's an arithmetic sequence or a geometric sequence. So you should be able to recognize which one it is. In this case, it's geometric. Okay, it's geometric, so we know what A1 is. A1 is the first term, which is 3. And R is the second, R is the common ratio, which is 11. What we need to find is how many terms there are, the number of terms. So we know that the first term is 3, the second term is 33, the third term is 363, etc. What we need to know is what the last term is. So we need n to use our formula for the sum of a geometric sequence. Okay, so we're going to go back to our general term formula that we have to find n. That is a sub n equals a1 times r to the power n minus 1. Now we know that n has to be a whole number. Maybe it's 15. Maybe that's the 15th term. Maybe it's the 12th term. I'm not sure yet. We can't just recognize it off the top of our head. At least I can't. So what we're going to do is use this formula, and the last term is a sub n. So the 643,076,643, we're going to let that be the a sub n so that we can find out which term it is. So that's going to go on our left-hand side. And then, of course, the a1 is 3 and the r is 11. That's going to go on the right-hand side. Okay, so there are a couple methods for solving this. Probably logarithms. That should look familiar. We did logarithms. We won't need to use logarithms because it's going to be a whole number. The other method is matching bases. So first thing we're going to do is divide by 3 on both sides. So divide both sides by 3 to get rid of the 3 on the right-hand side. Do that on your calculator. So on the left side you should get 214,358,881. Okay, so now once again we talked about logarithms or matching bases. You could do logarithms. You could take the log of both sides to bring the n minus 1 down in front of the 11. Or you could simply use your calculator and figure out 11 to what number is the number that we have on the left-hand side. I don't know that on the top of my head. Most people probably don't. Just play with your calculator. Put in 11 to the power 5. See if that's it. If it's too small, try a larger number. If it's too big, try a smaller number. Alright, so you should play around and you should get a power of 8. 11 to the power 8 will give you that number. Now that our bases match, therefore our exponents match. So we have 8 equals n minus 1, adding 1 to both sides, we get a number for n that is 9. So n equals 9. So that's the 9th term. Okay, we have all our numbers. We have a1, we have r, and we have 9. So now we can use our sum formula. So insert our a1, our r, and our n into the formula. And then use your handy-dandy calculator, and you should get 707,384,307. Okay, geometric series. Summation notation can be used to indicate the sum of a geometric sequence. When asked to evaluate a sum, write out at least the first 3 terms. So why do we want to write out the first 3 terms? The answer is so we could recognize which kind of sequence it is. Is it arithmetic or is it geometric? We have different sum formulas for each one, so we don't want to use the wrong formula. Okay, so let's start with I equals 1 and plug in I equals 1 and then I equals 2, maybe I equals 3. So that's 2 times 3 to the power 1 plus 2 times 3 to the power 2 plus 2 times 3 to the power 3. That should be enough to determine if this is arithmetic, geometric, or possibly neither. So 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. So now we have our first three terms, 6, 18, 54. Is this geometric? Yes, it sure is. Our common ratio would be 3. And that's because 3 is raised to the power of I. And our first term, a1, is 6. So now we have the information to use our formula. Our a1 is 6, our r is 3, and n is 9. The reason it's 9 is because it's the upper limit minus the lower limit plus 1. So the top number above the summation symbol is 9, the bottom number is 1. So 9 minus 1 is 8, then we add 1 to get 9. Whenever it starts out at I equals 1, then the number of terms is always going to be the top number. But it may start out at I equals 3 and then end at 27. So we need to use that little formula. The top number minus the bottom number plus 1. Okay, plug those numbers into our handy dandy formula. And then type it into your calculator. And it should give you 59,046. Okay, here's another one. Notice that this one has a lower limit of 4. So when we try to find n, we're going to use the top number minus the bottom number plus 1, or the upper limit minus the lower limit plus 1. Okay, so do the same thing. Find the first three terms just to make sure that this is geometric. So start with I equals 4, and then I equals 5, and then I equals 6. That should be enough. Two to the first, plus 2 to the second, plus 2 to the third, plus dot dot dot. So 2 plus 4 plus 8. Is that geometric? Yes. The common ratio is 2. If you divide a term by the previous term, you should get 2. So our A1 is 2, and our R is 2, and N would be 27. 30 minus 4 plus 1, 30 minus 4 is 26, plus 1 is 27. So N is 27. Plug those numbers into the handy dandy formula, and then into your handy dandy calculator, and calculate. $268,435,454. Okay, here's our last topic. This is on infinite geometric series. In other words, it goes on forever. Kind of strange, isn't it? That the sum of a sequence that goes on forever actually has a number. Well, it is strange, but there has to be a condition, and here's the condition, that the absolute value of r has to be less than 1. What does that mean? It means it has to be less than 1, but greater than negative 1. So it has to be between negative 1 and 1, and not 0. So 3/4 would be an example of what R could be. Or -2/5, or 0.3 if we're using decimals. If R is not one of those numbers, if it's not less than 1 and greater than -1, then there is no sum. So if R was 5, then your answer would be no sum. Okay, here's our first example. Find the sum of 12 plus 6 plus 3 plus ... Okay, so what is our A1? Our A1 is 12. And R, what is R? 6 divided by 12, or 3 divided by 6. So R would be 1/2. Can we use our formula? Yes. Because R is less than 1 or greater than -1, then we could use it. So plug those numbers into the formula. That's a little infinity symbol. So it's S sub infinity. That means it goes on forever. Kind of looks like a sideways 8. So you put the A1 on top, which is 12, and the R in the denominator, which is 1/2. And you could type that into your calculator. And you should get 24. So that means as you add these numbers, we're going to get closer and closer to 24. We actually don't get there to 24. It's an infinite sequence, so we have to keep adding more and more numbers. And they get smaller and smaller and smaller as we go. So that's why we get a sum of 24. Our last example. 3/4 plus 9/16 plus 27/64 plus ... Again, this is an infinite sequence because it just has a ... at the end, and it doesn't say the first 10 terms or the first 12 terms. So even though the problem doesn't say find the infinite sum, that wouldn't make sense, or it doesn't say in there anywhere infinite, you just have to know, oh, I got to use that S sub infinity, that infinite sum formula. Hopefully it's given to you on the test. Okay, so our A1 is 3/4, and our R is also 3/4. So if you take 9/16 and then divide it by 3/4, you should get 3/4. So A1 and R happen to be the same number. Plug those into our formula. Work it out on your calculator, or you can do it by hand if you want. You should get 3. Okay, that was it. I'll see you here for the next one.